the two small problems I put down. They are small in terms of text. This is not in itself very difficult if you know how to do it. This is easy to get confused, and particularly since I didn't explain several things that you need to know. So that gives me an opportunity to tell you what you need to know. Okay, the first thing is this. So here it talks about finding a density contrast at the time of entering the horizon. And it writes explicitly that you need this delta. And so that's what we did yesterday. Remember when we looked at how the overdensity evolves with time? We made these drawings. This is the case when it is smaller than the horizon, at matter radiation equality, and this is when it's larger. Okay? So now what we need to do is we need to look at this drawing and find out what was the overdensity when you were here at A enter, when it becomes smaller than the horizon. And if we start first with this case, it's actually quite easy, because you start here and then you evolve proportional to A squared until A enter. That's all. So you can then write this down. That's relatively straightforward. So lambda less than lambda equality. It's exactly what I did yesterday, except I'm going to stop at entering, time of enter. Okay, in that case, the density is the initial density times A enter over AI squared. Okay? It's just because here it is scaling as A to the second power. So delta goes as proportional to A. So if you relate it to where you started, it will only go up by that much. So that's fairly straightforward that we know that. Then we need to know what is this? What's A enter? And so what we did yesterday, and the reason why I'm doing this again here is because this is important in order to solve one of the problems for handing in. So what we did yesterday was we said the time it enters, the object, this is the size of the horizon at a given time. This is how far light can travel in T enter time, equal to, and then it has to be size A enter times the size of this object. And then you can do the same thing with the horizon at the time of AI. I would like to get rid of these AIs if I can. Ti is AI lambda I. So this is exactly what I did yesterday. And if you remember there, the next step was we used that the scale factor is proportional to the square root of time. Okay? So time goes as A squared. And that's very convenient because then I can divide these two equations by each other. And I get T enter over Ti is equal to A enter over AI squared. So that's this thing. Okay, that just goes in there. And that is equal to the ratio here. A enter, AI, lambda over lambda I. So now I've included the scale of the object. And this then means now I can use this put it in here, and I get delta T enter, delta of Ti times lambda I squared. Okay? So that tells me, given how big a structure it is, 100 megaparsec, it tells me how the overdensity is as it enters the horizon relative to what it started with. So that's one case. The other case is equivalent, is exactly the same thing. You do, but it needs one more term. So in this case, it increases like a squared from ai to a equality. So a equality ai, and then it increases linearly afterwards until it enters. So enter over a eq. So yesterday, the only difference is yesterday I did exactly the same thing, but I put a instead of a enter in this case. Okay. And so now I need to see if I can write this in the same form as I wrote this. And in this case, what you need is to need the other solution for the Friedmann equation you got yesterday, which was that a goes, let me just be sure, as 3/2, or no, sorry, 2/3. 2/3, or the time is proportional to a to 3/2. And now we can do exactly the same thing, write exactly the same equations. Ct enter, a enter, lambda, Ct equality, so exactly the same thing I did before. And you will get, in parallel to this, you get that a enter over a equality is lambda over lambda equality squared. And now we're almost there. The only thing you now need to realize is that this, here I could put a equality here if I prefer, instead of a enter. That's exactly the same if it entered at the time of a equality. So then I have a equality, ai is lambda equality lambda I. Okay, that's effectively this equation. And so if I now put this in, I get delta of T enter, so delta of Ti times this equality to Ai, that's equality lambda I squared, and then this term, which is lambda equality squared. And you see what I get here is I get exactly the same result. So you see the overdensity as things enter the horizon is exactly the same, shows the same functional dependence, regardless of what the scale is of the object. So that's the first thing, but that now depends on the scale. What we're asked to show in the problem is that this sigma, k cubed times the power spectrum, is independent of scale. in the case of a spectrum with n equal 1. So to do that, you write what that is. So sigma squared, or this, that's proportional to k cubed times delta squared. And if I put that in here, so remember lambda is proportional to 1 over k. So I can now put that in the equation there, and I get sigma is going to be proportional to first this thing squared, delta ti squared, times this term squared. So that's 1 over k squared times this k third power. Sorry. This is to the fourth power. It's second power and then squared. It's the square of delta that you need to put in. Okay? So this, we are told in the problem set that we can use a standard power law power spectrum. So this is Kn. This is K minus 4. And this is K3. So now you see this is proportional to the n minus 1. And so you see if n equals 1, this is constant with scale. Right? It does not, then it does not depend on k at all. It's just a constant. And the reason, one reason why this is actually important is that this also tells you the size of fluctuations in the gravitational potential. And that would be very nasty if the gravitational potential fluctuated arbitrarily large, either on small or large scales. Particularly on small scales, that would be really problematic. So this ensures that there are no extreme values of the potential variations in the gravitational potential as well. The other thing that's useful about this is that this is also something you get in the problem set. So in a slightly different setting, but you have to think about it very much in this way. And this is a straightforward calculation in principle. Is there any questions about this? Things you want to ask about? Because the next thing, there were several things in the next problem. There were at least 2 things that I had never told you about. So it would be hard to answer without looking at my lecture notes at least. So I'm going to define or explain those things first, and then I'm going to go to the problem set. Can I erase this? No? No? So there are 2 things in there that I used. And the first thing I wrote down was sigma 8. And that's something you will see a lot in papers on cosmology. People use this all the time. And the reason why it's important is that all the time what I tend to write is I write things like P of k is proportional to k to the nth power. So yeah, I write something like that. I write proportional to, and that's sometimes okay if you're interested in trends. But if you're going to ask how many galaxies form, you don't care about only this slope, you care about how high it is, right? Is it very low? You form no galaxies. Is it very high? Then you form a lot of galaxies. That's what you care about. So you need to be able to normalize it. And the question is then, how do you, thanks. It's going to take ages to come back up. Don't worry. It has some illness that when it goes to sleep, it really goes to sleep. Oh, that's quick. It clearly likes you more than me. Now, how do you normalize it? There's a number of ways you can normalize it. And the most popular thing is to use this thing called sigma 8. And so what is sigma 8? Sigma 8 is the, or sigma 8 squared is the variance of the power spectrum, or the density field, probably is the right thing, field on a scale of 8 h to the minus 1 megaparsec. So that all sounds a little bit weird, right? Why did we pick these numbers? And what does it really mean to call the variance? So this is a practical way of normalizing. Because if you remember how I introduced this sigma, I introduced it both in a way that you can calculate it from probability distribution, but also I calculated it as a way I make boxes on the sky, and I calculate the number of galaxies, or the mass of galaxies here, the mass of galaxies here, 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 and I calculate the mean and the standard deviation around that. And so this is a practical thing. You take spheres in the sky that are 8 megaparsec radius, plonk them on the sky, and you calculate the mass of galaxies, or galaxy clusters is what we usually use, inside there. And that should in principle give you sigma 8. In practice we do it slightly differently, but in principle that works. And so it's a practical way of calculating a normalization. And why 8 megaparsec? Well, it's 8 megaparsec because that's close to the scale where structures go nonlinear. So at 8 megaparsec, things are still in the linear regime, and you can use linear theory to calculate things more or less okay. Okay, and that's why we use 8 megaparsec. Okay, so that was one thing, and I will show you how to calculate it in a second, because that's part of the problem. So I'll come back to that in a second. The other thing is I talk about a 1 sigma perturbation. So let me generalize this and talk about the new sigma perturbation. That is when the overdensity, delta, is nu, or n, or whatever value you use, but nu tends to be the letter used in literature, nu times sigma. So you remember in many cases in these exponentials, we have this expression delta over sigma, right? It's delta c of time usually. This is usually a function of mass. And so when I say a 1 sigma perturbation, I mean when this is equal to 1. When it's a new sigma perturbation, this is equal to nu. And this, actually we know how it is if it's from this spherical collapse theory we had yesterday. So for spherical collapse, we have this is 1.69 times 1 plus z. So this means that our new version typically says that nu times sigma of m is equal to 1.69 times 1 plus z. So that's what a new sigma perturbation means. It means something that satisfies this kind of relationship. And where it comes from in practice is exactly the same as when you do, say, propagation of error in a lab course or something. We say that the likelihood of something is proportional to e to the minus x squared 2 sigma squared. And this is a Gaussian, and it's defined that when I give you an error bar, when I say a is 5 plus or minus 1, what I mean is that the likelihood of A is going to be proportional to e to the minus a minus 5 squared over 2 times, oh, let me call it 1.5 here, times 1.5 squared. Okay, that's what the error bars on a measurement mean. It means literally this. This is just a shorthand for writing down that the likelihood of a measurement has a distribution like that. And so then you can integrate these things up, and you find that the probability that A is between 3.5, A and 6.5 is 0.68. That's just an aspect of integrating this Gaussian function between those two limits, and that's plus or minus 2 times sigma, which in this case is 1.5. Okay, so that's what it basically gives you, some estimate of how crazy or how freaky it is. It's very easy to have something that's 1 sigma. It's not very far from the center. It's very unlikely to have something that's 3 sigma. So 3 times the sigma away from the center is very unlikely. It drops down very quickly because it goes as an exponential to the x squared. So it can drop down very quickly. All right, so now let's look at this in the problem. So it might get clearer, or maybe not. All right, so the question here was to ask about the mass of a 1 sigma fluctuation collapsing at redshift z, and what fraction of the mass has collapsed into objects with mass greater than that mass. So the first is actually very, very easy because we have done that. We did that yesterday. We wrote down the Press-Schechter formalism yesterday, and we said in that case that the PS, the Press-Schechter, tells us that the fraction greater than a given mass, which is z, is 2 times, it was that factor of 2 that they have no particular reason to put in, but it's there, integral from delta c of z to infinity. So it's all over densities greater than this collapse density, which we define from the spherical collapse model. And then here there's this Gaussian function again, 2 pi sigma of m e minus delta squared 2 sigma of m squared d delta. And we did this integral yesterday, and we showed that this, well, we didn't actually do the integral. I just told you that this is the complementary error function of the argument here. Square root of 2 sigma of m. So that's the fraction of objects with mass greater than m. And now we can do the very simple, now we can realize something very simple. Now we need to use this 1 sigma. So 1 sigma. I told you that means delta C Z sigma of m equal to 1. Which is very nice, because I can then put that in here. And I will find that the fraction I'm looking for actually, maybe I should put a star here, just to be clear. M star. Because that's what I use in the text. So the fraction greater than m star is a simple number. It's the complementary error function of 1 over square root 2. And it's independent of redshift. It's the same for every redshift. And this one you can plug into a computer. It's not the kind of thing that people go around remembering. It's 32%, or 0.32. So 32% of all halos have collapsed into halos that are bigger than a 1 sigma. Incidentally, that's, yeah, well, anyway, that's, the fact that it's independent of redshift is also very useful. Okay, so now that's the first question. We solved that. Now the next thing is we want to calculate the mass. What's the characteristic mass? And this is something that's practically quite useful. This is more a curiosity, which just gives you a way to calculate it. The next thing is to calculate what's the typical mass, because that's going to tell you what kind of objects form at redshift 0, 3, 10, 15, etc. And so that's the second problem. And so here, for this, we need to go and recall the one thing I showed yesterday, that sigma of m, we could estimate that with a power law power spectrum. And then this is proportional to the mass, to minus n plus 3 divided by 6. That's what we showed yesterday. What I used generally was divided by 3, because I usually use sigma squared, but you just take a square root and it becomes 6. Okay, so that's the first thing. The second thing, of course, is this. So let's just write this out first, just to see what this means. So then I will have to write this sigma of m is some constant, I don't know what it is, m to the minus n plus 3 is 6. I put that into this equation, and I get sigma, I don't get that, I get a times m okay, that's, I just written out what this means. So now you see you have, now clearly what you need to do, and this should be now, here it has to be m star, because now I've taken this to be equal to 1, so now this should be m star, and this is what we want to calculate. That's what this calculation is. If you wanted to calculate something that is a 5 sigma perturbation, or 3 sigma perturbation, or 20 sigma perturbation, you need to change this number, right? So if you wanted to put a nu in here, there would be times 1 over nu here. Okay, we're not going to do that here, but you could do that. So if I give you a question, what's the mass of a 3 sigma perturbation at redshift 3? You can calculate it. Or I can say, assume that the Milky Way formed at redshift 2, and what was it then, how many sigma was that perturbation? Was it a 1 sigma, 2 sigma, assuming that the halo mass of the Milky Way is 10 to the 12? So if I gave you that, I said, okay, redshift of the Milky Way formed at redshift 2. I put in 2 here. And I say, I think it, don't know exactly what it was. It was some perturbation. I tell you the mass of the halo of the Milky Way, 10 to the 12 or something. Then you can solve this for nu, and you can tell me, oh, the Milky Way was a 1 sigma perturbation or a 2 sigma perturbation. It will tell you how strange the Milky Way is. Right? It's a typical galaxy. But for now, I can't do anything more because I need to figure out what this A is. So the simplest way to do that is just to write it down, write this down for 2 masses. So what I'll do is I just write sigma of m, and the important thing here is that what I gave you is this sigma 8. I gave you the perturbation on 1 scale. So what I can do is I can calculate sigma of m over sigma 8. Or more commonly, what people write is they write sigma of m8. Okay? And so if that's the case, I will have m star over m8 minus n plus 3 divided by 6. Okay? So now I got an expression for my sigma. This one I've been given in the problem set. I gave it as 0.796. This one is something I want to know. And this one I don't actually know. So what's this M8? That's the first thing to calculate. And the M8 is the mass within a radius of 8 megaparsec. So let's do that first. Okay. So M8 is then 4 pi 3 R8 cubed, that's the volume, times the density. The density is the critical density times the mass, the mass, the relative mass density, so omega m times rho critical. And you can put in numbers. It's not, you just need to be careful and get the units right. And then you'll find that this is 1.54 times 10 to the 14, 8 to the minus 1 solar masses, times, and then just for reference, omega m 0.258. R 8 h to the minus 1 megaparsec cubed. So that's the mass within 8 megaparsec. Of course, given the numbers I had, you can ignore this scaling. I just put them in to be explicit about what the numbers is. So it's about 10 to the 14 solar masses. That's the size of a galaxy cluster, small galaxy cluster. And now we're almost there, right? Because now I can take this together with this, and I will find that, oh, dang, I erased, let me just, I erased the one equation from here I should keep. But anyway, let me write it down again. So sigma of m I wrote was 1.69 times 1 plus z. It's the one new parameter. That's this one here. Now I can solve this equation for m star. And I get m star over m8 is now sigma of m sigma 8 minus 6 over n plus 3. Okay. Or m star is m8 and I put in this thing, 1 plus z, 1.69 sigma 8 to the minus 6 over n plus 3. And so now you've solved it. Now it's just a question of putting in values. So 10 to the 14 for M8. The redshift I asked you about was redshift 0, 3, and 9. You put that in here. Sigma 8 I gave you. So everything here is given. N I gave you is minus 2.35. So what that now gives us is m star equal to 1.5 times 10 to the 11 at redshift 0, 4.1, 10 to the 5, redshift 3, and 8.7, 10 to the 1, so these are actually quite small things. They're quite small halos at high redshift. And you can see how they depend on redshift. They depend on redshift to 1 plus z to this power here, which is going to be relatively high. So it changes a lot with redshift. And so the typical halo at high redshift is going to be much smaller than at low redshift. And that's because this is a 6 divided by a number that's typically less than 1. So this is going to be, the exponent is going to be bigger than 6. So there's a big dependency on redshift here. So the mass of the halos actually changed significantly with redshift. And this then tells you, normally we use something, say 3 sigma as a more useful number, but it tells you a typical scale of galaxy formation. Yep? So what the case is that most of halo, maybe I wrote it down wrongly, but I don't think so. But because most of the halos that you see, the ones where galaxies live in, they form in significantly higher sigma halos than 1. They typically form in, say, 3 sigma halos. And again, this dependency of sigma comes in here to the same power. So if you go with 3 sigma halo, it goes as 3 to the 7th power more. So it goes up a lot in mass. So most galaxies actually form not in a 1 sigma halo, it's just a reference size. They form in, say, a 3 sigma halo, and then it's much bigger than 10 to the 11. Okay, so now I'm going to change away. What I was doing the 2 days now was dark matter. And I'm not going to forget about dark matter, but it is about time to move to something that's not dark matter. And I'm going to talk about cooling in the galaxies. So galaxies are formed of baryons, right? We all agree on that, I hope. That most of what you're interested in a galaxy is baryons, so stars, planets, human beings, etc. So the thing that helps you for collapsing is gravity. That's a good thing. What's a bad thing for collapse are things like pressure. Pressure forces resist collapse. That's the same thing as in Jeans analysis. Angular momentum is bad because you can't go down because you have too much angular momentum. So you stay there. And the expansion of the universe is also bad because that also go against your collapse. So there's nothing you can do about the expansion of the universe. No baryons can do anything about that. But the pressure is given, remember your ideal gas law, is given as nkt. And so if you can lower temperature, you can get rid of the pressure resistance to collapse. So that's why cooling is very important. And so let's go through very quickly which cooling pathways are important. And these are the main cooling sources that are relevant for galaxy formation. And let me go through them all one by one. So the first one is probably what you're more used to calling Bremsstrahlung. So it's free emission, free cooling. So electrons scatter off some ion, they change their path around the ion, and in that interaction they can lose some energy, and that energy is then radiated away as a photon. Okay, so that's Bremsstrahlung. That typically happens at very high temperature when the gas is completely ionized. That's when these interactions are important. And it becomes more and more important the higher the temperature is typically. The next one is free bound. So when you have an electron that combines with an ion and creates something that's possibly neutral or at least less ionized, and you give off a photon. This is very important as recombination radiation. That is very important because it tells us when galaxies form stars. And I'll repeat again what I talked about the first day later. But it isn't the most important thing for galaxies. The next one is bound free. That's when you basically ionize your atoms, and that can also be not containing here a photon, but it can also be leading to energy loss. The most important relation for energy, for basic cooling, is when electrons collide with atoms or something that have bound states. That's what it has to have. It can be ionized, but it has to have bound states. And you excite them. So you don't ionize it, but you lift electrons inside the atom up to an excited state. And then later these will de-excite and release radiation. Okay? This is the most important cooling relation in most galaxy scenarios. In addition, at high redshift in particular, you get inverse Compton scattering. So that's when the universe is full of photons from the cosmic microwave background, and the electrons in an ionized gas can interact with those photons and lose energy, typically lose energy. The situations where they could gain energy, but that's not irrelevant. So if they lose energy, that's known as inverse Compton scattering. If they gain energy, it's typically called Compton scattering for some random reason. And finally, it's Hubble expansion. Just expanding the universe cools it down. Expansion cooling. It's a standard way of cooling. So these are the main ones. So in a hot gas, most of the cooling in a hot gas in a galaxy context is Bremsstrahlung. At very high redshift or at very low density, or at relatively low densities, the main cooling mechanism is inverse Compton scattering. That's particularly important at high redshift, and you can think about that. The reason why that becomes more important is because the energy in the radiation goes as temperature to the fourth power. Temperature goes as 1 plus redshift. So as you go to high redshift, the temperature goes up by 10. The energy density in the radiation goes up by redshift to the fourth power. So this becomes important at high redshift. At very low densities, really low densities, the only cooling that is efficient, and particularly at low redshift, is Hubble expansion. It's the only thing that happens everywhere, and usually not very efficient, but at very low densities, this is the important thing. But in every other situation, the most important process is bound-bound. Okay, so we'll see some examples of what that means in a second. So the way it's encoded is we encode it in terms of cooling functions. So that we write the cooling functions in this way. Well, one way is similar to this or not. So E dot is the energy loss per time. So it's how much energy is lost from the gas. And we relate that to the cooling function lambda, and we typically take out the density squared on this side. The reason why we take the density squared out here, and people Unfortunately, there is no standard here. Here I took the total hydrogen density, so ionized and neutral. Some people take electron density times proton density, sometimes take electron density squared. Some people take ionized hydrogen density squared. It's a bit, you have to look up what definition people use, because those things make a difference, right? Electron density goes to 0 when the gas is neutral. Neutral hydrogen densities go to 0 when the gas is fully ionized, etc. So it's a nasty thing to, you need to get it right. Okay. So usually what people do is they calculate these cooling functions using some simple scenario. The most common thing is to assume the gas is static, there are no significant velocities in the gas, and that there is an equilibrium between collisions and ionization. So there's a collision-ionization equilibrium, and then you put that into a software package like Cloudy, and you get a cooling function out. That's not always sufficient for galaxies, but people use that simplicity sometimes. Okay, so this is what it looks like, a cooling function when you calculate it. This is for a gas that only has hydrogen and helium. And it is quite important to understand the various ingredients here and the anatomy of this. So the first thing that you notice is that it goes up. Well, I don't know what is the first thing, but at least one thing we can notice to start with is that as you go to higher and higher temperature, the cooling function goes up. And that is because Bremsstrahlung is dependent on the temperature to the power 1.5, more or less. It drops off as you go down here, partially because the temperature goes down. But this is actually only the temperature when I plotted this blue line here. It also will drop even more down because at some point the atoms, the electrons and the protons will combine and form neutral gas, and then you don't have any electrons, and you don't have Bremsstrahlung. The second thing is that you see there are two peaks and there's a drop-off. Okay? The first thing is the drop-off here. Let's look at this one first. That's at about 10 to the 4. Does anybody want to guess why the cooling function drops off at 10 to the 4? So it goes back, it's actually not entirely obvious. If this was in a galactic context, it might not drop off like this. And the reason why it drops off like this is that if you just have a gas that's a density of any gas in the universe, in sort of large scale universe, not inside a planet, for instance, the density is so low that hydrogen gas, if you excite hydrogen, it will de-excite, right? It will drop down. And all the levels in hydrogen have very short lifetimes compared to the time between collisions. So any hydrogen atom that you have, you might excite it, it might go up, but it will drop down again almost instantaneously for any practical purpose. So that means that your hydrogen atoms, every practical sense or reason, is going to live down at the n=1 level. And if you want to excite that, so you need to excite or ionize, right? Anything to get some cooling, you know, there's all these various cooling things, cooling functions here. Firstly, you need electrons, right? You could, I haven't drawn that here, but you could actually achieve this thing with neutral collisions. You could in principle do that, but in general you want electrons. So in order to get electrons, what do you need? Well, you need to ionize hydrogen. There's only hydrogen and helium here. So that means that you need something that can get you from n=1 to n=infinity, right? And that energy jump is 13.6 electron volts. And that's what we talked about the first day, that in order to get that, you need temperatures that are close to 10,000 Kelvin. So it means that in order to even get you need to go somewhere here in order to get electrons. And if you don't have electrons, you have no cooling. And so that's why this one drops off so quickly here, because suddenly you don't have any electrons. And so you can say, oh, well, maybe you can get electrons from somewhere else. Maybe somebody will just put electrons into your gas. Well, even so, the first thing, the only thing, so then you can say, okay, I don't need to do this step. I don't need to ionize my gas. I can just excite it. Which is fine, you can do that. That is the most important process after all. But to excite hydrogen, you're all down in the first level. The next level up, n equal 1, 2. This energy difference here, I never quite remember exactly what it is, but it's something like 10.4, I think, electron volts, right? Which is still quite high. So even to just excite hydrogen, you need you need a temperature that is of the order of 10,000 Kelvin. So if it's lower than that, I mean, if I plotted this with a logarithmic scale here, you would see that this extends down a bit. Okay? There's a bit of cooling down to a few thousand Kelvin, but the most of it, you need 10,000 Kelvin. Yeah.
This sounds a little contradictory, because to have a cooling process, you need to heat the gas.
Yeah. So you need to come from this side. Yeah. And so what this doesn't include is things like molecule formation. So what you actually have here is what you get normally when this curve goes down, it's easy, you cool, when the curve goes up like this, it's easy to cool, okay? You cool a little bit and then the cooling function becomes bigger, and you cool even more, and you cool very quickly here. So this way you go very quickly, this way you don't go very quickly, and here you go very quickly again, and here you don't go very quickly. So it means that basically gas tends to pile up in certain temperature ranges. And in order to go from here down to 20 Kelvin, which you need in order to form stars, you need to include molecules. And the cooling becomes much less efficient than this. This is super efficient cooling. But the stuff that you need further down here is much less efficient than this. But it will get you down to 20 Kelvin at some point. But you need molecules for doing it, and I didn't include them here. It's actually a bit of a nasty problem to get that right in hydrogen, because molecular formation of hydrogen is not so easy. So. Okay, so that's the cutoff. So the cutoff basically says you need at least 10,000 Kelvin gas. This process won't work very well in gas that's much cooler than that. It will just hang around. But now you have the other thing here, and that is you have these two peaks. So what are those peaks? Well, what I said, and I'm not going to let you go until you remember that, is that the main cooling mechanism in sort of galactic gas is bound cooling. So it's things where you excite an atom. Okay, so what happens then? Well, the first thing, if you just think about hydrogen, okay, what you can do in hydrogen, you always start in the ground level. And what you can do with hydrogen is you can knock it up to the first level. You knock it up to second, third, fourth, fifth, etc. until you reach infinity. Then you've ionized it. So I can sort of lose energy at any level up until I've ionized hydrogen. When I ionized hydrogen, there are no bound states in hydrogen anymore. And that means that the only range of energies where I'm really efficient is when I can keep hydrogen neutral. So this is the range over which you have the various levels in hydrogen, from 10.4 electron volts up to 13.6 electron volts. So it's just a narrow range, and that's only when there are bound states. You go to higher temperatures, hydrogen is ionized. And helium is in this peak as well. The first electron in helium is in the same peak. And then the next thing that happens is that you heat the gas up, but now there are no bound states in hydrogen, and you don't have enough energy to excite the second electron in helium. That doesn't happen until you get up to temperatures that are around 100,000 Kelvin. And so this is the second electron in helium, and eventually you get so much energy that you also ionize helium completely, and then you have no longer bound states. So these sharp peaks, they basically correspond to bound levels in atoms. And they are a generic feature of any cooling function. Might not be that this bound, depending on the density, depending on other conditions, bound transitions might or might not be the key cooling effect, but mostly that's what it is. So that's for hydrogen and helium only. It's convenient to have because sometimes if you look at very high redshift, that's what you have. What about adding metals? Well, you get this. So this is now the cooling function for a solar metallicity gas. And you can see it's now a logarithmic axis here to show the details a bit better. And the previous one I had is this dashed line. See this? Goes up here, goes up here. So it's hydrogen and helium, peaks. Now the full cooling curve is this. It's quite a lot higher. The black one is the sum of all. No, it's the sum of all these other ones. So the sum of all the elements together makes this black solid curve. And then it's broken down into the individual elements.
So, but to get that black curve, you need to sum all.
So the way it was calculated was that first they ran the simulations including all the elements, and then you get this black curve.
Okay.
And then they ran the simulation turning off all elements except one of these. And they actually add linearly. So the sum of these colored curves actually becomes the black curve. So it's just because there's no significant interaction between them, but at some level they will be slightly different. And now you can see several things, okay? First, you see that the peaks, again there's peaks, and they're there exactly for the same reason as the peaks are in hydrogen and helium. They're bound states in the atoms, okay? So, and then the other thing you can notice is that you have carbon here, oxygen here, neon here, iron here. They're all shifted to higher end temperatures or higher energies. So do people have a feeling for why that is? Why you shift them, typically shift them to higher energies? So if you think about Coulomb force.
Yes. It's just electromagnetic.
Exactly. So it's just these things have more charged, their nuclei have a higher charge than hydrogen. And so your Coulomb force, your Coulomb binding energy of the electrons goes up as the charge squared, right? Z squared, in just standard Coulomb law. So as you go up in charge of the atoms, they typically peak shifts to the higher energies.
Electrons are more linked.
Yeah, they are more strongly bound at for the higher numbers, exactly. It doesn't fully, it's not obviously explaining everything, because for instance you can see sulfur is here, which is where it should be, but it also has a peak here. Iron has a peak here, another peak here. Iron has lots of mess here as well. And that's more details of atomic physics about what's going on. These are more shielded inner bound states in sulfur that have a much higher ionization energy.
Why do you have elements with two different bits, for example, silicon and sulfur?
Yeah, so sulfur is here, silicon is that one. Yeah. So it is because some of these. So it has to do. So this stuff I never remember off the top of my head. Has to do with whether you have complete shells or not. So the elements that have complete outer shells have very tightly bound inner orbits. And so what you have is you have these ones that have a complete inner shell, and they just very well shielded until you get enough energy, and then you start ionizing those.
That depends on the exterior electrons.
It depends on the distribution, electron distribution in the various shells, and whether your shells are complete or not. And so sulfur, silicon, and also iron to some extent have this configuration that makes the inner bound states more shielded. But I don't remember all the details of that, though. Never use it. So the other thing that's very important to notice here, and that should be very clear, is that this cooling curve and that one, they differ in absolute value. When you have more metals, you can cool your gas a lot better, a lot more efficiently, and at a lot higher temperature. So if I go back to the previous plot, I would say that basically anything above 1,000,000 Kelvin, it's very hard to cool down. Okay, the cooling curve is very far down. It will take me a long time to go. And if I cool down a little bit, the cooling becomes even less efficient. So it's very hard to cool down this one down to a low temperature. And the same thing here, of course. Here I cool off, it's more less efficient, less efficient. And so it means that typically in this gas, you will have at least 3 phases. You will have a phase that's typically about 10 to the 4 Kelvin, because it's hard to cool down here. You will typically have one that's about 10 to the 5 Kelvin, because it's hard to cool down here. And you would have a hot phase that's about 1,000,000, a few million Kelvin. This is a bit more, will have a more spread in temperature. But here they will be kind of isolated around a bit of a temperature. So you could approximate your gas at zero metallicity as consisting of a high temperature bit, 10 to the 5, 10 to the 4, and then whatever else managed to cool down really cold. And so you have the multi-phase medium. Usually simulations do not like that, so they don't tend to ignore the fact that it's multi-phase, but reality is going to be multi-phase. It's going to have multiple temperature components. At higher metallicity, you can see the cooling can be efficient, like at the level of, just a little bit below the peak here, out to very high, much higher temperature, 10 to the 7. So you start getting efficient cooling even at very high temperatures. And you can cool very quickly from a few million Kelvin because the cooling curve goes up. So it becomes more and more efficient. You cool it a bit, it's even easier to cool, even easier to cool, even easier to cool, and you get rid of this multi-phase structure. Is not going to be the same, although it still will have something around 10 to the 5, and it will still have something around 10 to the 4. There will still be this multi-phase medium, but it will be much less here in this 1,000,000 Kelvin range. So this cooling efficiency and metal abundance is very important. It means that formation of stars, formation of galaxies is going to be different at zero metallicity and at significant metallicity. It's going to be much easier to form something to get rid of excess energy, get rid of pressure at high metallicity. So as soon as you can start producing metals, your galaxies will form much more easily. So it's difficult. It's possible now in simulations, but it was for a long time difficult to form the first structures because it's very difficult to cool the gas down. So people needed to look really carefully about how to cool the gas. So you can observe this cooling then comes out in various emission lines. I've talked about them earlier, I'll come back to them later. There's a range of different lines here that are all over the spectrum, and you can find out what's happening. So here is a comparison of this now using a linear scale. It's a bit easier to interpret and without all these colors. So you can see solar metallicity, 50% of solar, and metal-free gas. And you can see how the peak here, which is due to hydrogen, mostly, that doesn't change very much because metals are not a big contributor to, they can't compete with hydrogen. There's so much hydrogen in the world that hydrogen will dominate, and then this peak doesn't change very much. Most of the metals have transitions at higher energies, and they have a lot more electrons. That's also very important. You put metals into a gas, and they can produce a lot of electrons for you. So a hydrogen atom can only give you 1 electron, right? Whereas iron might give you, depending on the temperature, might give you 10 or 15 per atom. So they produce a lot of electrons. And so this really changes things at the high temperature range, as I said. Now, you remember yesterday I put this equation down for the virial temperature. I wrote it down again here, but I see I didn't put it in. Let me also insert the value for R. So this virial temperature we showed yesterday, this virial radius depends on the mass to 1/3 power. So the virial temperature depends on the mass to the 2/3 power. Okay? So as you go up in temperature, so as you go up in mass, you have a bigger dark matter halo. Your temperature goes up almost linearly, but not quite. And if you want to form objects in it, a galaxy inside that halo, you need to be able to cool. And this is a characteristic temperature, right? So see now, next slide I think has that. I put in numbers yesterday. I found that in the Milky Way-like halo, the temperature was about 100,000 Kelvin at redshift 0. A Milky Way-like halo at redshift 3 would be 4 times that. So getting close to 1,000,000 Kelvin. And that means that the Milky Way cooling curve is somewhere in this regime. Okay? And this is part of the reason why it's efficient to form stars in the Milky Way type halo. If I had a much bigger halo, say 10 to the 8 solar mass, 10 to the 8 Kelvin halo, so mass that is 10 to the 15 or something, then it's very inefficient to cool. And so it makes it harder to create stars and galaxies. So that's part of the reason why, as you remember, we had this plot showing, and I'll show them later today as well, showing that it was inefficient to form stars in Milky Way-sized halos. The Milky Way, on the other hand, is close to the peak of the cooling curve, this kind of halos. So here, when you put baryons into them, the baryons will heat up to, say, a couple of 100,000 Kelvin. It will be around here. And then depending, as long as there is some metals in there, it will actually cool very quickly, to some extent. So that was one thing. Okay, that was a simple case when the gas is fixed. It's not, I mean, if you have Cloudy running on your computer, it's not very difficult to run a calculation like this. But that's not really what the universe is like. I mean, when you create a galaxy here, that galaxy is not going to be completely isolated from everything else. There are probably going to be stars formed in it, and those stars will then affect the gas. These cooling curves assume that there's only collisions, that there is no radiation onto the gas. That's not very realistic. You almost certainly have a source, if you form stars, you will have a source of ultraviolet photons. So what happens when you turn on ionizing photons in here? So this paper here did this to prepare for some simulations. So this is their cooling curve without sources of radiation. And this is the cooling curve with radiation. Okay, and just go back and forth. You can see there are several changes to it.
It's not so easy with radiation.
No, not at all. One thing, the first thing that you will see perhaps, well, it's a mixed blessing. The first thing, look at this hydrogen peak here. It's gone. Disappeared completely. So the reason why this disappeared is that you cannot answer why it disappears without some more information. Okay, if I put the sun here, it wouldn't look like this. The reason why it disappeared is what they call radiation sources here are defined as stars, could be something else, but in this case it was stars that are hot enough to ionize hydrogen. By definition, that's what they put in. So since these stars, they shine on the gas. They shine on the gas with hard ultraviolet radiation, and that radiation is strong enough or energetic enough to ionize hydrogen. Okay? And I said earlier that this peak is due to bound transitions in hydrogen. You need to have a bound transition So when I ionize hydrogen, I lose it. It's gone. There's no bound states in hydrogen anymore. So it does not, this doesn't exist. This peak, right, that has changed a bit. It's moved a bit to higher temperature, but not completely gone. And that's because stars, very few stars have enough energy to ionize helium twice. Some stars do, but very few of them. Essentially only Wolf-Rayet stars and a few very, very hot white dwarfs can do it. So this is mostly untouched. Now, if I had done, and I don't have a picture of that, if I had taken something more energetic, I'd taken an active galactic nucleus, a black hole, center of a quasar, and I put that in. That has a lot more ultraviolet photons to much higher energies. And what this would do, it would basically wash away a lot of these. Right? It will destroy bound states in helium, neon, and oxygen completely. You will still have cooling in iron, but you will get rid of a lot of these cooling functions. So you would get a very different scenario, and it will be very hard for that gas to cool down. So you will have a lot of hot gas around these that don't cool down to become stars or galaxies, clumps of cold gas. The other thing that you notice, or maybe you didn't, but you will now, if you now look at the low temperature part, see, it goes down a bit, but you see what it does? It extends. It extends to lower temperatures. And the reason it does that is, anybody want to guess?
You showed the maybe just a little bit.
Mm-hmm. So you can also see another thing which will give you a hint, perhaps. Look at this line. This is Bremsstrahlung. It depends on the electron density squared. You see it moves slightly, very, very slightly up. Now imagine you have a cold gas, okay? It's a cold gas, so everything is neutral. And then I turn on a sharp ultraviolet light on that gas. Okay, so I'm down here on this end. So the gas in itself is really cold, has nothing in it. And then I turn on my source of UV radiation. And what happens? Well, what happens is that I will create electrons. Right? I will ionize some hydrogen, not all, but some of it. I will ionize it from my radiation. And that means that I have electrons, free electrons, and the cooling function, the cooling processes, like bound free, bound bound, as long as you have electrons and neutral particles, you can start creating cooling. So you need electrons. You really need electrons somehow. In this case, it's because you've shown a UV light on the gas. So the UV light ionized the gas, created free electrons that then can run around and collide. If your gas is hydrogen only, then you're not going to get very much of a tail. And that's because there are very few bound states. It's very unlikely to excite hydrogen at very low, very low levels with electrons. You have electrons hitting the hydrogen, but they have to be able to get enough energy into the hydrogen to lift it up to the first excited state. But it's much easier when you have metals, because there are many not so strongly bound transitions in metals, and that's why this tail goes much higher. So this is actually very useful. Any way that you can create electrons is super useful for cooling the gas. So you can shine a UV light on it. That's one way. The other way is what I said yesterday. if you change the virial temperature of the gas, your gas particles would move with enough velocity to hit each other sufficiently hard to excite hydrogen. So if your virial temperature is above 10 to the 4 Kelvin or so, you might have no electrons, you might have no radiation sources, but just by the fact that your halo has that mass means that you can crash the electrons together, the atoms together, and create cooling. And that's thought to be the way that you can cool and create the very first stars in the universe. And they will actually form in halos that have virial temperatures of about 10 to the 4 Kelvin, and the temperature high enough to create free electrons and hence start cooling. So these functions are not very suitable for analytic calculations, as you might see. They're complicated functions. When you desperately want to put them into a problem set for students, what we do is we approximate a little bit of this with a power law. And of course, that's a bad approximation. What they are used for in reality is you put them into computer calculations. Of course, in a perfect world, what you do is you solve these equilibrium relations everywhere in your simulation, but that's very time consuming. So people, instead, they create these lookup tables and they say, okay, I got a gas particle that's 10 to the 6 Kelvin. Now let me look at the cooling function. It's about 10 to the minus 22 ergs cubic centimeter per second. So now I can calculate how much energy is going to be lost by that gas particle. And then I can add in energy that comes from somewhere else. And I would probably then look up and see, okay, I have this particle is being shown on by stars with so and so much stars. And I can then use this cooling function, or I can use one that's relevant for something else. And then I use that as a lookup function in my simulation to get it right. So in hand calculations, you don't do it. Right. And the other effect, which I forgot to mention. The other effect here is if you look at the high metallicity, the effect is relatively small of the radiation. There's a little bit of an effect, but it's not very much. So it means that the effect of radiation in very massive halos, so think now instead of temperature of the gas, think about the x-axis here as the mass of the halo through its virial temperature. So this is massive, very massive halo, very low mass halo. And you see that in massive halos, the effect of radiation is going to be much less than in the low mass halos. Okay. So where does this come in? Let me just see where I'm in the proceedings. Okay. So where does this come in practice in terms of galaxy formation? Now we're really going to talk about galaxy formation. Like we're in the dark matter halo. Well, there are three time scales that basically compete. And it's easiest to think about formation as a competition of different time scales. That saves you from solving a complex coupled set of equations. The first thing is the expansion time of the universe. Okay, that's one time scale. It gives a time scale of doubling of the size of the universe. The second one is the free fall time scale. That sets the time scale of gravitational collapse. It's the same time scale that you normally would use in a genes analysis of a star formation. I will typically just use that it goes as 1 over square root of g rho, because it's a bit arbitrary how you calculate that. And finally, it's the cooling time, because that gets rid of pressure support. And that one you can calculate depending on the ionization state. This is for a fully ionized single species gas. And then you will get an expression that depends on density, temperature, and the cooling function. So this is where the cooling function comes in. It sets this time scale. So now you have this competition between these time scales. So when does galaxies form? Well, they form when this cooling time can dominate, right? When you can cool quickly, and this becomes the longest time scale in the problem. So here are the different time scale situations. You can have a situation where the cooling time of the gas is longer than the expansion time of the universe. Well, at that point, it's no point, right? The cooling, it's taking so long that the universe has doubled in size by the time it's cooled a bit. So then you get no collapse. The intermediate stage here, which is when the cooling time is longer than the dynamical time, but shorter than the Hubble time, so then you can ignore the fact that the universe is expanding. Then what happens is that it cools a little bit, but then the gravitation can re-establish pressure balance. Sorry. So it can basically put you back in pressure balance again very quickly. So gravitation can quickly re-establish equilibrium. And so what happens in this case, and I'm not going to go through the argument in detail, but what's happened in this case is that you basically move slowly along tracks of constant Jeans mass. So this collapses, but it collapses slowly. It's not a very efficient way of doing anything. What's really good is when the cooling time is shorter than your free fall time. Because then they're basically, while you're collapsing, the cooling removes pressure support quicker than you can collapse. So the only thing that's left is gravitation. So it's as quick as gravitation can collapse, basically. That's what you want. This is efficient formation, and there's no pressure support that's stopping you from collapsing. And that's the various time scales. Then you can plot these different time scales in diagrams to get a feeling for what's happening. And this is an example of this. So this is going to take me a little bit to go through this plot in detail. So on this axis, it's the density of the gas. On this axis is the temperature of the gas. These lines are constant gas mass lines. And I also written down at what redshift this density leads to collapse. So that's the collapse criteria that I gave you yesterday for the virialized collapse. The delta greater than delta critical times some large delta. It's a bit stupid actually to call it large delta since it's delta times delta, but anyway. So these means that at very high redshift you get very high densities at collapse. Okay, that's the background. This is a zero metallicity, and what these lines here are, this black line you can recognize. It's just the cooling curve turned on its head, right? This is the line where the cooling time is equal to the dynamical time. So this depends on temperature and density, and the dynamical time essentially depends on density, right? It's 1/square root of density. And so when you are above this black line, the density is high enough. So the more dense the gas is, the more efficient can it cool. All the cooling functions depend on density squared. So the higher up you're here, you're above, you can cool really efficiently and things can form. When you're below the black curve, you're in a situation where you can't cool quick enough. So there's no collapse on the outside. And this red line is when the cooling time is equal to the Hubble expansion time. So again, if you're below this one, then the universe expands more quickly than it can cool, and nothing is going to form. So here is the same plot now, but now using solar metallicity, and you can see how it changes. If you go back, you can see it doesn't change very much at the low temperatures, but it does change at the higher temperatures, and you can get lower densities, can you start getting efficient collapse. If you compare it to the mass tracks, you see basically at the 10 to 13, the track of 10 to the 13 is always below the black curve. It can never cool fast enough to form. So in early days when we thought all galaxies just formed in a single clump collapsing, this actually gave you a very, and it's still mostly true, this gives you more or less the reason why objects with mass greater than 10 to the 13 do not exist. Right? Why there are no galaxies with mass 10 to the 13? Because the time it takes for them to cool down is too long for them to have collapsed to objects in today's universe. Whereas 10 to the 11, that's inside here. So objects of mass 10 to the 11, they can cool fast enough relative to gravitational collapse to form an object. Okay? So this is the main reason why there is a maximum limit to galaxies. Previously we talked about dark matter halos. We saw there was a cutoff in the mass function. But this is about galaxies. This is about cooling baryons. And it says that there's just not enough time to cool a gas that's of a galaxy that's 10 to the 13 to have formed a galaxy today. It's the main reason why. And here is sort of I've just illustrated the bits of quasi-static and where it can be collapsed. And there are some extra parameters that go into the specific calculations here, but they're not very important. So that's what this phase diagram really is quite important for. It tells you what kind of galaxies can actually form, and that's quite a nice little result. The other thing which is cute about this, particularly if you're into numerology or something like that, but it still is kind of cute. So a galaxy is a big, galaxy or galaxy cluster is among the biggest structures in the universe. What sets this line is the cooling function. The cooling function depends essentially only on atomic parameters, right? So you can make a calculation here. If you set these things equal to each other, you pick some typical scale here. You put these two equal to each other, and you can get an expression for the maximum mass of the galaxy in terms only of atomic parameters and g, because gravitation comes into play. So it's actually the maximum mass of a galaxy is expressed in terms of quantities that describe the smallest particles in the universe. And it's kind of a cute result like that. Anyway, it has absolutely no useful meanings. I'm not going to show you the equation here, but it was derived some long time ago by Oestreicher in some paper in the 70s.
Sorry, Joe, but you were saying that this mass is not including dark matter.
This one is not, yeah. This mass is this relationship in the calculations that I did. I actually adjusted the dynamical time scale for dark matter because it makes a difference. But baryonic matter makes up 20% of the gravitational potential. So you're going to change this by a factor of 1.2 back or forth here. So you're not going to see it on a logarithmic scale very much. So this one does take into account dark matter, but the maximum would be very similar. And the original calculation was done before people realized there were dark matter. And so it's using only baryons, and you get more or less the same number within some factor of 2. Okay. Right. So this is just re-emphasizing this 10 to the 12 is sort of on the limit, and it isn't quite good enough because, if you formed your galaxy from very, very many small pieces and put them together, then this argument wouldn't hold completely, at least. But it tells you, at least what it does tell you is that in a halo of a temperature of 10 to the 7, that gas that's in that halo it's going to stay around there. It's going to be so these halos are going to be full of gas of 10 to the 7, 10 to the 6, 10 to the 7 Kelvin, because it hasn't had time to cool down yet. And when you go outside and you look at the sky with an X-ray telescope, you actually see that gas. It's in essentially every galaxy cluster in the sky has hot X-ray gas. Not all of You can't always detect it because it might not be bright enough, but essentially all of them have. And that is because they have that gas, but it cannot cool down because the time scale is just too long in here to cool down. It's typically hot and relatively low density, so you have absolutely no chance of doing it. And that's why galaxy clusters are so full of hot ionized gas. You see it everywhere. So this cooling function is really essential for a large number of cases. So the next cooling is now on bigger scales, because that also matters. And what we're going to talk about now is the role of inverse Compton scattering. So this is basically a situation where you have a gas with lots of electrons, and you have photons getting into this gas, and what happens is that if the electrons here have higher energy than the photons, what will happen is that, so these have typically large velocities. What will happen is that these electrons will change in velocity, so effectively lower the temperature, and the photons will have gained in energy, so they have now higher energy photons. Okay, so that's a cooling process that's taking energy from the electrons and dumping it into the cosmic microwave background. And the cooling function is this one there, which so I'm not going to derive the equation, which is du gamma dt equal to 4 kb MEC sigma t. And I remember NE. Okay. Okay. So it is derived. It comes from Companet's equation. If you want to actually derive it, it's not a particularly pleasant derivation, and it doesn't tell you anything interesting. And this tells you what the energy in photons, how that changes depending on the depending on the temperature of the electrons and the temperature of the photons. So you see, if the electrons have higher temperature than the photons, then this is a net gain of energy for the photons. If the photons have higher energy than the electrons, then this is a net energy loss for the photons. So this is the energy loss equation for photons. Now, the energy of a photon gas is A times T gamma to the 4th power. So you can put that in here. And you get a proportionality to NE to T gamma to the 4th power, and then T minus T gamma. Okay? So that's just the proportionality of this equation. I just removed all other things. Now, there are two important things here. One is that all the cooling processes that I talked about, except for this one, all the things that I've talked about before, has an electron hitting something else. All right, so it depends on the density of the electrons and the density of the other particle. So a density squared. So as you go down to lower and lower densities, it becomes much less efficient because it depends on density squared. This process depends only on density to the 1st power. Right? So this process will be efficient at much lower densities than all the other cooling processes because it only depends on density to the first power. So that's one important thing. The other important thing here is that you can now assume that the electrons are really hot. Let's assume that. That's kind of useful because the cosmic microwave background today is a bit less than 3 Kelvin. At redshift 9, it's 30 Kelvin. And I'm interested in things that are 10 to the 4 Kelvin. So with a good approximation, TE for our needs here is going to be much larger than gamma. Okay? In other situations, this differs, of course, depending on the physical conditions. In that case, this is proportional to the electron density, electron temperature, and this still remains, okay? And to the photon temperature to the 4th power. And this temperature here, that's the temperature today, 2.73 Kelvin, times 1 plus Z. Right? That's the evolution of temperature which we did the first day. So that means that our energy loss is going to be proportional to any TE T gamma 0. Well, that is not so important. It doesn't change. And then 1 plus Z to the 4th power. And those are the two crucial things. One is that it depends on the density to the first power, so it's really efficient even at low densities. And the other thing is that it depends on the redshift to the 4th power. So that means that at high redshift, this is going to be a lot more powerful than at low redshift. So this is a crucial bit to put into calculations at high redshift. But what people do in simulations is that they include this cooling source at redshifts greater than 6, and then they turn it off because it becomes completely irrelevant because it depends so strongly on the redshift. So the final thing is that you can then calculate the cooling time. And that's the cooling, the time it takes to cool, we define to be energy divided by energy loss, which have units of time. And I've actually written it there on the slide, so maybe I can just use that so I don't make typos. The energy of the gas is density times temperature, kT, times the number of electrons. This is the energy per electron. This is the number of electrons. And then you divide it by the cooling, which we calculated is proportional to NE, TE, 1 plus Z to the 4th power. How did that happen? I must have touched it here. And you see the cooling time goes as 1 plus Z to the minus 4 power. So it's much, much shorter at high redshift. And it's independent of density. As long as you have electrons, this cooling doesn't care about the time it takes to cool the gas down by, from 10 to the 4 to 10 to the 3 Kelvin. It's independent of density. It doesn't care about density. The typical time here, I didn't include the numbers here, but the typical time scale here of this cooling time at redshift 0 is about 10 to the 12 years. So the universe is 10 to the 10 years, more or less. So 10 to the 12 years is a very long time. So at redshift 0, this is absolutely and completely irrelevant. You don't ever need to think about it. But it goes up as the 4th power. So if you go to redshift 9, this is 10 to the 4, right? So then your time scale goes down from 10 to the 12 to 10 to the 8.
So hundreds of millions.
Yeah. So this cooling time becomes important at redshift 10, and if you go to even higher redshift, this becomes one of the most dominant cooling effects. Yeah.
Sorry, but all of these masses assume that the unrecommended is 0.
No, none of this will affect angular momentum. So all of these relationships are insensitive to angular momentum at the level that we care about here. So no, that wouldn't change anything, because if you think about what happens in a there are a few situations where direction of collision matters. So if you're doing a relativistic calculation, so then you have the equivalent of the Compton scattering will have, in that case, it matters what direction you hit things. And then it could have some dependency on angular momentum, that you will predominantly cool gas with one type of angular momentum or another. In general, it matters relatively little. Okay, it isn't, angular momentum doesn't matter at all in itself, because these processes, all of these processes are independent of angular momentum. You conserve angular momentum through all this. So cooling never affects angular momentum. If I have an object that moves around on an orbit here, and I cool it down, it will not collapse, because the angular momentum will stay the same. But if I have objects that move on random orbits like this, and I cool them down, then they will collapse down, because they will lose velocity dispersion. But angular momentum is conserved in all these processes. There is a situation where it matters, but it's not very important in most cases. But it has to do with velocity in the gas. So let me plot the cross section of an emission line. So let me take hydrogen beta. Okay, that's centered on 4,861 angstrom. Okay, that's the peak of that. And it has a cross-section for absorption that's Lorentzian, but very sharply peaked. It's around that wave value. Now, so what happens is that if I move the gas, okay, I might or might not be able to absorb photons of some sort. So cooling cases where photon absorption becomes important, like to create electrons, then velocity gradients might matter. Okay? So I change the velocity, I might or might not get an efficient process, but the emission of this is independent of angular momentum. That's just an atomic process, a quantum process, that doesn't care about your angular momentum at all. So in all these equations here, oops. Let's see, where were they? Here. All these equations here, everything here is atomic physics. So as long as they can hit each other, they don't care about the angular momentum. The angular momentum of the particle will be conserved, at least as long as that isn't conserved in the quantum case. But the actual process here is independent of angular momentum. So angular momentum won't matter, but the flip side of that is also that these processes cannot affect angular momentum. So if you have angular momentum, you cool it down, it won't help you at all. So angular momentum is not affected by these processes at all. Okay, so I got a bit shorter than I thought I would, but that's okay. So what I'm going to do now is, well, after the break, I'm not going to start on it now because it's a completely different topic. What I'm going to do next is looking up how gas goes into dark matter halos and how potentially it gets out of dark matter halos. And that will happen after 2. And to illustrate that, there will also be quite a few movies. So we will look at a few simulations in order to get a better feeling for what's happening. But this is then for after the break. I'd hope perhaps I would finish this before the break, but it doesn't really matter. I have one section tomorrow that I left free, so I can adjust.
So we'll see this after lunch.
After lunch, yeah. You will not, but.
Missed.
Okay.
Tengo sustentación de mi concurso, sé que la cosa. Mientras yo estoy allá, ustedes están aquí con las vellitas.
All right. Thanks.
See you later.
See you later. See you after lunch.